Okay, student, here we shall see about the torque which is experienced by a current loop when placed in a uniform magnetic field. So as you can see here, this is a rectangular loop PQRS, and the current which is passing through this loop, let's say it is I. Okay, so this current here, it is flowing in clockwise direction. Okay, now this loop, it is placed in a uniform magnetic field B, which is acting from left to right. Okay, all right. So if you remember, when we talk about area, any line which is drawn perpendicular to the area, like this line, so this line means normal to the area. So in this case, the normal to this plane of the loop PQRS, the normal is this line. And this normal here, it is, it makes an angle theta with the field. Okay, so now what happened here is, because we have seen before that when a conductor, okay, is placed in a uniform magnetic field, and if there is a current passing through the conductor, then such conductor carrying current when placed in a magnetic field always experience a force. Okay, so now in this rectangular loop PQRS, we have four sides of the loop. One is a side PQ, which carries a current in this direction. Next QR, next we have RS, next we have SP like this. Okay, so when we look at these two conductors, PQ and RS, okay, so the current along PQ, okay, it is in this way. Now if this current I, it is passing in this direction, so if you treat this side PQ of the loop as a single conductor which carries a current, then this side PQ will experience a force. Okay, but if you apply Fleming left hand rule, all right, now this is the the directions of the magnetic field, which is actually given by the four fingers of your left hand. The directions of current along PQ mean, right, it is along this side, and this thumb will give you the directions of magnetic force. So that means this side PQ will experience a magnetic force, right, along this direction. Okay, so let's say this is F1. Okay, similarly the sides SR, okay, it is carrying a current run along RS in this way. Now if you apply again Fleming left hand rule, then you will find that the side RS here, it experienced a magnetic force but in the downward direction. So let me name that as F2. Okay, so now these two forces, F1 and F2, they are acting along the same, line. Okay, this is a line. F1 is acting up, F2 is acting down. So these two forces, they are acting along the same line, and this line is actually the line of rotations, or we can say the axis of rotations of the loop. Now such forces which is acting along the same line, okay, then they will not produce any any torque, because torque is actually a rotating force which happens when the two forces are acting at the two ends of the line in different direction. Okay, so here what we found here is the magnitude of the two forces F1 and F2, it is same, and the directions is different. One is up, another is down. So therefore these two forces, they will cancel out each other, and finally this sides PQ and RS of this rectangular loop will not experience any magnetic forces. Okay. Okay, now when we look at another side, SP and QR. the directions in this side's SP, it is acting up, right? So if you apply again Fleming left hand rule for that, you'll get directions of magnetic field, directions of current is up. So the directions of magnetic force, it is usually represented by the thumb of the left hand. So the force in this case, right, it will be directed inward. So that means this side of the loop, it will experience an inward force, and I will name that force as F3. Okay, the sides QR, it carries a current in the downward direction. So again, by Fleming left hand rule, this side QR will experience a force, but this force, it is directed upward, okay, perpendicular to the plane. So I'll name this force as F4. Now what is the magnitude of these forces? F3, if you remember the force which is experienced by a conductor when placed in a uniform magnetic field, it is equals to ILB sine theta, where theta in this case, right, it is the angle between L and B. So the angle between, right, when you look at this conductor SP, the angle between L mean along this side SP, and B, it is from left to right, so the angle is 90 degree, so sine 90 will be 1. So you'll have only ILB. Now what is this L for the sides SP? L for the side SP, it is equals to, I have, assume here to be B. Okay, so this is the magnitude of the force F3. Similarly, the magnitude of the force F4, it is equals to IBB. Okay, now these two forces, they are equal in magnitude but opposite in direction. Not just that, when you look at the lines, right, the line of actions of these two forces, one force, it is acting in this way. Let's say this is a force F3 and this is a force F4. Now these two forces, they are acting along this sides, right? If you join, okay, something like this, so along this line. Now these two forces acting at the two ends of the line in opposite direction, so they will constitute what we call it as a torque. Okay, so this torque, it is denoted by the letter tau, which is a Greek symbol, and it is defined as A the force times the perpendicular distance between them. Okay, now when I say either force, it means you can write either the force F3 or F4. So tau here mean, when I say either force mean, it may be, right, it is the same, magnitude is same. If you write F3, it is IBB. If you write F4, so it is IBB. So same thing. So the magnitude of either force, it is IB capital B times perpendicular distance between the two forces. Now what is the perpendicular distance between these two forces F3 and F4? So when I say perpendicular distance, it means from this point, if you drop a line in this way, and from here also you drop a line in this way, such that the two lines intersect perpendicularly at this point. Okay, suppose I'll name this as point M. Let's say this is A, this is B. Now this sides AB here, it means this sides from here to here. So from here to here, it is actually the side small a. Okay, that is small a. Okay. At the same time, okay, this is the directions of the magnetic field B. And this small n, I mean capital N, which is normal to the area, it is acting in this direction, and this angle is theta. So when this angle is theta, right, you can also say that this angle is theta. So now what is the perpendicular distance between the two forces F3 and F4? Okay, the perpendicular distance between these two forces, right, one force is like this, one force is like this, so perpendicular distance means this line. So in this case it is MB. So now how much is MB? MB here, it is equals to A sine theta. Okay, if you find out sine theta in this right angle triangle, okay, then you'll get like MB is equals to A sine theta. Okay, so because of that, I will say perpendicular distance between the two forces, which is actually equals to MB, or I can say tau is equals to IB, capital B. Instead of MB, I'll write A sine theta. Or this tau here, it is equals to I. Now I will rearrange the term AB. I'll put them inside bracket, and then I'll write B, and then sine theta. Or tau here is equals to I. Now what is this small a into small b? A into B, it is the area of the rectangular loop. So for that area, let me write it as capital A. So IA B sine theta. Okay. So this is the magnitude of the torque which is experienced by a rectangular loop PQRS when placed in a uniform magnetic field B. Okay. Now, if this loop PQRS, let's say it has n number of turns. Okay. So for n number of turns of the loop, what will happen? This torque can be written as n times I A B sine theta. Okay. So this is the expression when there are n number of turns in the loop. Okay. Suppose this is my equation 1, this is my equation 2. Alright. But you will see later that this NIA, it is equals to small m, which we call it as magnetic dipole moment. Okay, so for this we will see it later. Okay, so therefore instead of NIA, I will write, okay, tau is equals to small m B sine theta. So this becomes the new equation for the torque experienced by a current loop. Okay. Or in vector form, I'll write tau is equals to m arrow cross b arrow. So on top of this tau also I have to write arrow because I'm talking about a vector. So because this tau here is a vector, it means it has a direction, and the directions of this tau, okay, it is actually the, it will rotate, or it should be perpendicular to the plane containing both m arrow and b arrow. Now the question is, where is the directions of this m arrow? This m arrow, it is actually along the same as the directions of the normal to the plane of the loop. Okay, so I think this is clear to you, right? So now we shall see about a special case from this topic, and the special case is when theta, case number 1 is when theta is equals to 0 degree or 180 degree. So looking at this equation number 3, tau is equals to mb. When theta is 0, you put sine 0 will be 0. If you put sine 180 also, sine 180 is 0. So tau is equals to 0. So what does it mean? It means that when theta equals 0, so look here, theta equals 0, it means that this normal to the plane of the loop, it is acting along the same as the directions of the magnetic field. This is the normal. Magnetic field also is acting along the same direction. So in that case, theta is 0 degree. Or when the normal, it is acting like this, but the magnetic field opposite to that, the angle between them is 180. So in such cases, when the plane of the loop, it is perpendicular to the magnetic field, then that loop will not experience any torque, which which means the loop will not rotate. Okay. Case number 2. When theta is equals to 90°, then again from equation 3, you will get tau is equals to mb sine 90. But we know sine 90 is 1, so 1 times mb will be just mb. And this is known as the maximum value of the torque. Okay, so in other words, I can say when theta is 90°, it means the loop, this is the normal. And if the normal it is facing that side, that means the plane of the loop it is like this. The normal is acting in this way and the magnetic field is this way. So the angle between the normal and the magnetic field is 90°. So in such case, this this loop will experience a maximum torque, which means the loop will rotate maximum. Okay, and it will rotate in this way. Okay, so the rotations of the loop in this case, right, it will be in the clockwise direction. So please remember this point here, that I'll just remind you quickly that when a current loop is placed in a magnetic field, then that current loop always experience a magnetic torque, which means the loop will rotate in a magnetic field in the clockwise direction. Okay.